In the last example of this section, let us produce the expansion of this indefinite integral into a power series. So assuming that we're content with having the antiderivative of this function expressed as a power series and not in the closed form, we can very easily produce such an expansion using the theorem about integration of power series. And so indeed, what we can do is we start by representing the integrand here by power series. And so 1 over 1 plus x to the 7th can be thought of as 1 over 1 minus x to the 7th, which has the form 1 over 1 minus x with x replaced by minus x to the 7th. And so since we know how to produce power series expansion for this function, we write that down. It's the geometric series k from 0 to infinity, sum of x to the kth. And then we must replace the x by the minus x to the 7th here. So this is the power series representation of the integrand in our indefinite integral. Let us simplify this further and determine when this series converges. You can rewrite this power series as the sum minus 1 to the k times x to the 7k. So what we did here was we simply thought of minus x to the 7th as minus 1 times x to the 7th, and then raised this product to the kth power. Now, when is this series convergent? Let us think back to how we obtained it. We obtained it as a geometric series with r being minus x to the 7th. And so it must therefore converge when the r in this geometric series has absolute value less than 1. This is the same as to say that absolute value of x to the 7th is less than 1, or that absolute value x to the 7th is less than 1. Then if you take the 7th order root of both sides of this inequality, you conclude that absolute value of x must be less than 1. Great. So what we have here is we have shown that 1 over 1 plus x to the 7th is equal to the sum of this power series when absolute value x is less than 1. Now, since we want to represent the integral of this function by power series, what we have to do is to integrate both sides of this equality. So we take this relation and integrate both sides. On the left-hand side, we will have integral of 1 plus x to the 7th as desired. So this is the function we wanted to represent by power series in the first place. On the right-hand side, we have to integrate this infinite power series. And this equality holds for x's with absolute value less than 1. Now, by the theorem about integration of power series, we know that to integrate a power series, all we have to do is to integrate every term separately. So this expression in the right-hand side is the same as the infinite sum from 0 to infinity of the integrals minus 1 to the k x to the 7k dx. Let us go ahead and integrate these integrals. This factor here is independent of x, so we can take it outside of the integration. And then we are looking at the sum of the constant factor minus 1 to the k times the integral of x to the 7k dx. Now, it suffices to integrate this expression, and this is of course just a power function. To integrate a power function, all that we have to do is to increment the exponent and divide by it like so. You have x to the 7k plus 1 divided by 7k plus 1. K from 0 to infinity. And then we will add the constant of integration. So we are effectively taking all the constants of integration from all this infinite number of integrals and combining these constants into a single constant of integration here. Now, since the original equality had this power series which converged for all x's in absolute value less than 1, this power series here will also converge when absolute value of x is less than 1. So this is of course because integration preserves the radius of convergence, and starting with a series that has radius of convergence 1, right here, this is saying we have power series centered at 0, obviously, and convergent in an interval with radius of convergence 1. And so integration preserves that radius of convergence, and so r is equal to 1 here as well. So as usual, we do not say anything about convergence of this series at the endpoints of this interval. So the endpoints of the interval of convergence, and I want to emphasize this, can change after integration. So the original series converged on the open interval from -1 to 1. So I will leave it to you as an exercise. Show that the new series, meaning this one here, converges at x equals 1 and diverges at x equals minus 1. Finally, let us write down the answer to this example. So we have computed the antiderivative of 1 over 1 plus x to the 7th in the form of a power series, minus 1 to the k, x to the 7k plus 1 over 7k plus 1, and plus the integration constant. And so this equality here between the antiderivative and the power series holds for absolute value x less than 1, as we discussed. In fact, it even holds for x equals 1, but not for x equals minus 1. But that requires separate consideration, and we do not obtain it automatically from the theorem about integration of power series. The theorem only tells us that the radius of integration is preserved, and so that gives us this equality here on the interval from minus 1 to 1. This form of the answer is particularly convenient if you are only concerned with the values of this antiderivative on this interval for x. So of course you could have done this computation using partial fraction decomposition. So you could have written down the partial fraction decomposition for this function, then determined the coefficients, then integrated, and that would have given you the form of the antiderivative in as a closed expression. That closed expression would be defined outside this interval as well. And effectively, if you're concerned with values of x outside of this interval, that is what you would have to do. On the other hand, if you're fortunate enough and you're only dealing with this antiderivative on this particular interval, then you can save yourself a lot of effort by going to the integration of power series, and you would have obtained the answer as we just did.